All right, hello everybody. I'm Valerie Suchins, and I'm here with my partner, Jonathan Massey, and we make up Team Iradion, which is focused on automatic laser optimization and production. So right now, a laser technician will use a long screwdriver to turn these 3 screws in the laser resonator in order to align this fully reflective mirror with the partially reflective mirror on the other side of the resonator. This alignment is critical for the laser beam attributes. So our best anticipated outcome is to first do this alignment, but automated, while it's connected to an autocollimator. The mirror, which is then aligned, is then transferred to the laser resonator, which is then optimized for alignment in order to follow the power output. It's also important for the laser technicians to know the torque that is being exerted onto these screws, because if they are overturned, the mirror will warp and be useless. So the outcome we came to, we are able to do the pre-alignment with the autocollimator, as well as monitor the torque using a calculation in the C# program, which will use the encoder voltage output of the motors in order to calculate this torque. Unfortunately, we were unable to test this with the laser, as we created a method for the power output, but we're still in the debugging process. And so next, I will show you a quick video of the alignment using the autocollimator. So this is the crosshair of the mirror angle as it is being aligned. It is then trying to be centered into its optimal alignment. And once the program is completed, it will let you know in the GUI. Okay, I'll stop doing that. Yep, okay, there we go. So here's the block diagram of our communication flow in the system with the autocollimator. So the C# program does all of the calculations and will take the feedback from the autocollimator and then transfer this data to the FPGA using a UART. The FPGA then sends the control signals to the drivers, which will then send those commands to each motor in order to figure out which one to be turning as the alignment is done. The output voltage from the motors are then sent through an analog to digital converter, which will then calculate the torque. The power output is shown here, but is not implemented into the autocollimator system, but is shown just to see where it'll be implemented when using the laser. So the hardware that we had to do, we had to change the motors to servo motors, and we did not really have any experience with motor and driver systems before this. So we had to do a lot of extensive research into figuring out how to control these. So the motor we decided to implement is this hybrid servo, and the direction and pulse signals are controlled by the FPGA, and we output the motor voltage from this encoder in order to calculate the torque. So this is just a setup of our entire driver and FPGA system, showing the communication of the signals to the pulse and direction, as well as where the UART and the analog to digital converters are placed.
To begin, we will look at the FPGA and the processes that it undergoes when communicating between devices. It will start by receiving what motor to turn, which direction, and how many steps to turn that motor. It will send that through the UART to the FPGA. The FPGA will then decide which driver to send it to, and the driver will let the motor know. Then when the motor is turning, it will receive that voltage signal back to the FPGA, and the FPGA will then use the UART again to send it to the C# code, and all the calculations are done in the C#. In C#, we also created the GUI. At the top, you can see the X and Y position of the autocollimator in real time. And the GUI allows the laser technician to decide whether they want to go based off turns or torque output. Next, let's look at the logic on how to decide which screw to turn when attached to the laser. Neither of us really have any experience when optimizing lasers, so we talked to Iradion's laser technicians, and they went over the directions in which the mirror was tilted when turning each screw. The top 2 screws will turn in the X and Y direction, whereas the bottom screw will only turn in the Y direction. This is important to know because we have to decide which screw to turn each time. When turning the screws, the laser technicians will look at the power and the shape of the beam. Unfortunately for us, we can only look at the power output, which will be a voltage. This is the ideal voltage curve that we were following, and this is a top-down view where the rings represent the points going up the curve. In the middle is the peak voltage that we are looking for. The problem that we run into is the laser is not ideal, and it generates these waves going up the curve and causes multiple maxes and mins that can catch the program in. The goal is to move to the y-axis and then down to the x. This is a simple state diagram of how we design the logic for which screw to turn. We start off by receiving the starting voltage from the laser, and then we'll start by turning screw 1. And when talking to the laser technicians, they will always turn the top 2 screws and then reference back to the third one so they don't fall too far away from the x-axis. The process will start with the first screw and then reference the third one, and then when it goes too far, it will move on to the second screw loop and then finish up in the third. Some mechanical accomplishments that we have is we extended the back end of the hex bits to help ease the insertion of the hex bit into the mirror mount. We also added a track system to allow the laser technicians to easily slide the machine forward and back so they can change out the mirror without having to move a giant machine. We also had to create a new base that has a dip down so it is level with the laser and the autocollimator. A problem that we ran into is the laser mirror is rotated 90 degrees from the autocollimator, so we had to design a new middle part to hold the hex bits to account for this. We would like to thank everyone who helped and supported us on the project.